Oh, hey! Welcome back to A View from Earth, brought to you by the Fiske Planetarium at CU Boulder. We hope you're all staying safe and doing well. As with the rest of the university and many public spaces around the world, Fiske's theater is closed to the public for the foreseeable future due to the COVID-19 epidemic. However, we are still so committed and excited to bring astronomy and education to you that we've started a whole host of free online offerings so that we can stay connected and keep bringing you the Fiske content you know and love, plus some new stuff like this podcast. So thanks for tuning in and learning with us here today. My name is Colin Sinclair. I'm a CU student. I'm a presenter at the Fiske Planetarium, and I am a co-host of this podcast.
And my name is Tara Tomlinson. I am a planetary scientist and a CU alum, and also a presenter at Fiske Planetarium. I also coordinate our community outreach program, and obviously co-host the podcast as well.
This week, we'll be talking about black holes. Now, these are some of the most intriguing and elusive objects in the universe, and astrophysicists have done an amazing job of studying them and sharing their findings. Today's guests are Jimmy Negus and Dr. Andrew Hamilton, and they'll be answering the questions, what is an active galactic nucleus, and what is the interior of a black hole like? But first, the news.
All right, so for our news segment this week, we have our friend Rami here with us. Rami, why don't you introduce yourself? Tell us a little bit about you.
Hi, I'm Rami. I'm an astronomy student at CU Boulder with Colin and Tara, and I work at Fiske Planetarium as a presenter usually.
Awesome. And I hear you have some cool black hole news to share with us.
Boy, do I. So, as a news anchor, I have made it my mission to track down, you guessed it, anchors, but also news. And I just so happen to have the topic, some about the topic at hand, which is supermassive black holes, which is such a coincidence, I know. So word on the street is that some compact objects like neutron stars or stellar mass black holes have heartbeats, not from pumping blood, but from eating material. It's called a quasi-periodic oscillation, say that 3 times fast, and it happens when a black hole has an accretion disk, it's eating stuff like you can see behind me. So the intensity of, say, X-ray emissions ends up with a bit of a beat to it, a particular frequency, a fairly regular amount of time between peaks in output. It's not a terribly uncommon event, interesting, and can tell astronomers a lot about what sort of system they're looking at, and kind of give an idea of the mass of an object, but it's not really a miraculous find in the long run. But why is this news, Rami, you ask? Well, dear listener, what makes it news takes a bit of digging. Firstly, this sort of event is extremely uncommon in supermassive black holes, the ones at the center of galaxies, like you've been talking about. So smaller black holes, that tracks, but even the most extremely energetic active galactic nuclei don't often have these oscillations, these heartbeats. So the number of galaxies that have this can be counted on your fingers, which isn't much compared to the number of active galactic nuclei that we know of and have observed. So that's noteworthy. Make note. The reason it's news and not notes, however, is because there's a pretty neat case that they very recently published some data on. So the first galaxy to have these quasi-periodic oscillations, or QPOs, measured is called REJ1034 plus 396, which is catchy. So REJ10, REJ, it's Reg for the moment. Reg's QPO was first identified back in 2007. The X-ray oscillations were on the scale of about an hour, and again, pretty unexpected. So they continued observing this galaxy for a few years until that pesky sun caused some troubles, preventing proper observations from 2011 all the way through 2018. Data were taken again, finally, in 2018, and the results were published just last month. And it turns out that oscillation is still going strong. That's a pretty long time to have such a regular heartbeat. So generally, QPOs are a byproduct of those feasting compact objects. But to have such a regular pulse for such a long time, and for such a large black hole, this one a few million times the mass of the sun, it's pretty exciting. So according to Professor Chris Doan at Durham University, these pulses are likely indicative of maybe change in size or shape of its accretion disk, expanding and contracting. So this sort of behavior has really only been seen in a stellar mass black hole feeding off a companion star. So a black hole on the scales of like 100,000 times smaller than this one. Though no particular cause has been identified and confirmed as of yet, they're looking into it with anticipation. The paper's lead author, Dr. Qixuan Jin, who rightfully calls the heartbeat amazing, believes that this will provide the best opportunity for scientists to further investigate the nature and origin of this heartbeat signal. So next on the to-do list is to keep up with the analysis and do some comparisons with those similar behaving stellar mass black holes, which means it's a developing story, an active mystery. So keep your finger on this black hole's pulse because it's got plenty to tell us.
Fabulous. That's really, really cool.
Definitely is.
Cool. Wow. Yeah, I had no idea that black holes had heartbeats. I didn't know that for even stellar mass black holes. So thank you for putting that research together and sharing this with us.
Absolutely.
So our first guest for today is Jimmy Negus. This is excerpts from a recording we did a couple of weeks ago. So hope you guys enjoy our chat with Jimmy.
And today we are going to be joined by Jimmy Negus, who is a PhD candidate at CU Boulder, studying active galactic nuclei, or referred to as AGN, with the Sloan Digital Sky Survey, or SDSS, which is a telescope survey. And with this survey, he can analyze the light from 10,000 galaxies to identify signatures of movement and composition in their bright centers. So, Jimmy, did you want to add anything to that or correct anything I
think that was a beautiful explanation. I obviously think AGN are the best objects in the universe.
The best.
And I look forward to discussing more about, sort of our attempts to understand their nature and their impact on galactic evolution.
That is very cool. And I love how you put it on your website. I love the sentence that you wrote out that says, at the core of each galaxy, there exists a supermassive black hole, a dense cosmic region with a mass equivalence of up to 1 billion solar masses. That's just so pathetic. I like how you put that. But just to clarify, so do most scientists now think that every galaxy has a black hole at the center?
Every massive galaxy. So the exception, of course, you have dwarf galaxies or irregular galaxies. So you can think of objects like the small Magellanic Clouds, the large Magellanic Clouds. For objects like those, it has not been confirmed that at the center of all of those entities, there exists a black hole. But what has shown in the literature with very, very strong consistency and evidence is that supermassive black holes do occupy these inner regions. And, of course, it's astronomy, so we can only provide the strongest consensus. It's a scientific process, so it's always under constant review and evaluation. And so that's why nothing is 100% definitive, but we strongly believe that this is the case for our massive galaxies in our universe.
Okay. Cool. I like that because, it's one of my favorite things to tell people is that black holes are not like this rare exotic thing. They're kind of everywhere.
There are many believed to exist in our own galaxy, just at a much smaller scale than the supermassive ones. And when I say supermassive, what I mean is by 1 million or more solar masses, the equivalence of a black hole's mass. That once you reach that threshold, you are then considered supermassive.
Let's bringing it a little closer to your research. You specifically look at active galactic nuclei, the center of galaxies. So how is an AGN different than a black hole specifically?
Indeed. So an AGN is where things, it's no holds barred. It's where things get very interesting. And what we have is usually most galaxies host quiescent or quiet black holes. So they exist at the center of these galaxies, and matter, tends to orbit around them, but they don't cause too many problems. However, if you have perturbations or disturbances or things become uncomfortable for that black hole, so you can think if say a merger is underway, or if you have collisions of massive compact objects. If you have turbulent events, what can happen is this supermassive black hole can begin to accrete matter violently around this black hole. And for about 10% of the cases, we believe that very powerful electromagnetic radio jets can stream from the axis perpendicular to the plane of the galaxy. And so what we're seeing in these active galactic nuclei is essentially particles that follow strong magnetic field lines. But to answer your question directly, an active galactic nuclei is when active accretion, which is just the rapid funneling and spilling of matter directly onto the sphere of that black hole, once that begins, we consider that galaxy active. And for reference, our own black hole, Sagittarius A star, is a quiescent galaxy. So we believe that it is not active, but it's not to say that it cannot become active or that it was active at some point in its lifetime.
Okay. So, and that's another question that I get all the time with, you know, we hear about these bursts and these radio jets and things. If these black holes are so dense and have so much gravity that like not even light can escape this, how is this huge jet of radio energy coming out of it?
Of course, of course. So we have entirely different processes at effect. And so the gravitational force is actually one of the weakest forces in our universe. And what is stronger than that are electromagnetic forces. And so what happens is you're having particles, dust, gas, you have stars, baryonic matter that is funneling around this black hole, but these are all electrically charged particles and states of matter. And what happens is when you rotate these electrically charged particles, you create magnetic field lines perpendicular. And this is actually much stronger than the gravitational force that's trying to pull the matter in. And so what you're having is an interplay between this matter and the magnetic field lines that's overcoming the force of gravity. And these are actually some of the most powerful signatures of the universe that are usually observed in X-ray and have velocities that can approach fractions of the speed of light. So these are very, very energetic and powerful radiation that we're observing.
Yeah, but for now we can study the spectra, the light and the energy that's, you know, around that black hole and coming out of the AGNs, which is what you do. You look at the light that's reflecting off of there or being emitted out of there. So what kind of things can we learn from the spectra of these AGNs? Indeed,
indeed. So spectroscopy is an astronomer's best friend. You know, unlike many sciences, physical sciences on Earth, you know, we can't just go to a laboratory and measure properties we want. So we have to rely upon our observations. And of course, these objects are extremely far, and we can't just send a probe to a black hole. So our best friend is, how can we analyze the light that is emanating or produced by these objects? And through spectroscopy, we can attempt to gain some understanding about the fundamental physics of what we're seeing. And in particular, AGN are known for the extremely fast cloud velocities that orbit their black holes. And so the first sort of telltale sign that you're viewing an AGN, particularly if you're looking at it pole on, is we'll notice very, very broad emission lines. And broad emission lines correspond to the velocity of the matter that's orbiting these black holes, or that's being ejected from these black holes. So one of our best friends is studying a lot of the spectral lines. And for my project in particular, I'm looking at the ionization states. So when an atom becomes ionized, we're effectively stripping an electron. And in order to strip electrons from certain species of matter, it requires abundant supplies of energy. And we believe that there are certain highly ionized species that unambiguously correspond to active galactic nuclei. And so my project is, can we hunt down these ionized gas signatures so that we can better find these AGN? And that is the true challenge, is finding the AGN, because we would love to study them. We would love to learn their properties, but we're learning that it's hard to find these AGN. You know, in some cases, there's not enough light that's being emitted for us to detect. And so similar to black holes that are quiet, we try to infer the presence based on the response of the matter around it. And so my project is really getting at the heart of understanding the behavior of the matter that AGN are interacting with.
So even though these things are, you know, super active and bright and fast and everything, they're still difficult to find.
So a caveat here is they're very bright and they're very active, but what we have is other processes that can mimic AGN. So they're very bright, but imagine if you had an AGN that is millions of light years away, and let's say you had a supernova, you know. So what happens is you can have supernova remnants that mimic these AGN signatures because they're also very bright, powerful events. And given the distance, sometimes it's hard to infer which one is which. And most of our advances in the field of AGN study rely upon the ratios of prominent emission lines to determine this, if it's an AGN or not. And this is due to the energies, like I said, that are required to produce certain lines. The problem with that is, again, you can have star formation contaminate a lot of these ionization ratios because fast outflowing energetic processes tend to mimic each other. And so it can be very challenging. And this was actually the foundation. So AGN are called quasars, which the root of that is quasi-stellar object. And that was because we didn't know if they were just very bright stars or if they were actually what we know today is active galaxies. So it's a very challenging field, but spectroscopy is an astronomer's most valuable asset in terms of peering through the night and really resolving some of the mysteries of the universe.
Yeah, it's definitely my favorite thing all the time. Yeah, just I think it's crazy that just by seeing the different ways that light can be emitted from something, you know, hundreds of millions of light years away, like you can look at it and tell if that's grass or astroturf, you know.
It's really crazy. Cool. It's crazy. It really is fascinating.
Awesome. Well, I'm going to pass it back over to Colin. He's going to ask you some more, not personal, but just more questions about you as a scientist.
Of course.
So yeah, as Tara said, I like to always go back and you know, it's fun to kind of learn about the backstories and kind of your personal story. How did you get to where you are working on all this cool stuff? So that's my question for you. Did you always want to study AGNs or black holes or astronomy in general? Or you know, you discovered about yourself?
Indeed. So this truly started in 11th grade for me, where I built my first Dobsonian telescope. And, you know, I really just knew I had a broad interest in astronomy. I wanted to study the stars. I wanted to learn more about our origins and the greater context for how our universe is woven together. You know, what are the fundamental laws dictating it? I wanted to see what the true extent of our backyard was. And this motivated me through college to study physics. I knew I had to get the fundamental understanding of the physics and math. And a lot of students I have, you know, they get into astronomy and they just want to see pretty pictures. And that certainly is a part of it. But the fundamental underpinning of that is understanding the physics and the math. And so I went to University of Chicago and I got my degree in physics with a specialization in astrophysics. And my interests were still pretty broad. And I actually, after undergrad, took a few years off. And I studied, I actually assumed a position doing engineering at a company in Boulder, Colorado, working with atmospheric profiling, right? It's you know, it's small scale astronomy. It's very local. But I knew after a few years that my true interest was returning to the cosmos. And in particular, a thing that fascinated me was high energy astrophysics. And the root of this interest is the influence. High energy astrophysics can literally change the very basis of a galaxy. It can alter its very evolution. And so everything that stems from that evolution, from planetary science to astrochemistry to astrobiology, are all, to me, symptoms of the high energy processes that determine the structures and their behavior. And so to get to the root of high energy processes, what better than AGN? You know, these are some of the most powerful objects, some of the most distant objects that power a lot of the galaxies that we observe. And so for me, it was really just wanting to understand more of that. And the process was working closely with my advisor and discovering I really loved observational astronomy. I really loved not only understanding the physics, but seeing, you know, the objects that were compelling me so. And so really observational astronomy and AGN sort of found me. And, you know, as I understand more and more about AGN, the more I learn about, you know, everything about astronomy and astrophysics. It really has a huge, expansive trickle-down effect. And it's been a pleasure to see how it connects and how that web really links to other events in the universe.
Yeah, so now we're going to transition into our questions from the public segment. We're calling this CAPCOM. People are reaching out to us and we're relaying their messages to our expert.
Excellent.
So we've got some questions from the public that we're going to throw at you, see what you think. So the first one is from Mick in Boulder. He wants to know, what's the tiniest black hole we know of, and do we still think micro black holes exist?
All right, so the tiniest black hole is on the order of a few solar masses. And so these are black holes that can arise from the stellar evolution process. So they are very tiny, but they're nothing compared to micro black holes, which are still, from what I understand, theoretical objects. And so I'm not sure if many of you are familiar, but CERN, there were concerns about, you know, are they going to create a black hole and destroy the Earth? And so let's think about the most famous equation, E equals mc squared. And so if we're talking about a black hole, we're talking about a dense concentration of mass, which is equivalent to a high abundance of energy. So mass and energy are essentially equivalent. And so you could consider, if we had a very energetic process, such as two particles smashing into each other, could we create a micro black hole? And the theoretical minimum size of such a black hole is known as the sort of the Planck mass, would be the mass of such an object. And that's about the mass of a flea egg, for reference. And these are purely theoretical. And it has long been suspected that we don't even have the energy capabilities to create such an object. And if through some crazy act we did, it would survive for 10 to the negative 24 of a second. So it would be it would evaporate instantaneously in essence, because its mass is so small and it could not sustain itself. So it would essentially evaporate almost immediately.
So that actually,
going back.
Sorry, Tara, go ahead.
What I was going to say, and kind of going back to what we talked about earlier, black holes are not like these infinitely sucking things. There's only so much that it can do. And if it's
exactly,
size, we're probably not in any danger.
Exactly. So we're safe for now, folks.
Excellent.
For now.
For now.
Jimmy, your response to that question actually leads perfectly into our next question, which comes from Vince in New York State. Vince asks, you know, all I know about Hawking radiation is that it makes black holes evaporate. And so the first question is, if nothing can escape through a black hole, then how can they evaporate? If that information is destroyed, then, you know, how can it kind of come back in that way? And second of all, if they can evaporate, and if the black hole we saw recently, M87, is 53 million light years away, is it possible that it's gone by now at its point in space? Because what we're seeing is 53 million years old.
Excellent. These are great questions. And so Hawking was a great scientist who studied black holes, and he evoked the theory of Hawking radiation. And so essentially, there is a quantum law called quantum unitarity. And essentially what that means, what the law dictates, is that no information in the universe can just be lost. It must be accounted for or traced in some form. So as we're all familiar with, energy is conserved. So if something disappears, the logic is that energy is somehow just transmuted to assume a different state. And so that is sort of the fundamental backdrop for Hawking radiation. And so Hawking radiation, to resolve the information that is lost in a black hole, posits that as a particle enters a black hole and is lost forever, to preserve the signature of that particle, there is an antiparticle that is emitted in an opposite direction. So one goes in and is lost, one comes out, an antiparticle. And the theory is that Hawking radiation it accounts for this radiation that to an observer would seem to be lost from a black hole. And over long enough timescales, the equation suggests that a black hole can actually evaporate over long enough timescales. However, the theory also suggests that the order is longer than the time of the universe for a typical black hole to evaporate. So again, we're talking about billions and billions and billions of years to theoretically evaporate any sort of moderate or massive black hole. So yeah, no, it's very certain that black hole did not evaporate on the time scales. What is far more likely would be, say, a merger, or if the AGN turned off or turned on. These are much more reasonable on our cosmological timelines.
So when we talk about the little micro black holes that we were discussing from that first question, you mentioned that, it would almost instantaneously evaporate. Yeah. Is that through the same process of Hawking radiation, or is that something else going on there?
So my understanding is those are just inherently unstable processes. It's not massive enough to really sustain itself in the first place. So I'm not an expert on micro black holes. I study the big guys, but my theory is that they are two disconnected processes, and it's more of a stability issue because we're creating energy almost instantaneously, and that black hole just cannot sustain itself long enough.
Got it. Thank you.
No problem.
And so I think we talked about this next one a little bit, but I'll throw it out there again because Ray in Austin wants to know about the distortion of space-time and how does that affect the motion of other kind of cosmic bodies moving around the vicinity of, like you mentioned, this trampoline with the huge dip in it. Do we directly see that sort of motion happening?
Indeed. And it's most traceable by simply looking at light. So light is obviously, it's how astronomers view the universe. And so what we've noticed is through gravitational lensing, if we have distant stars and galaxies that are emitting light, and there's a black hole in between us and those sources, we'll notice that the light itself becomes distorted. And that is a property of the black hole. Its gravitational influence is literally bending that light. And in similar processes through gravitational effects, you obviously have stars that are tidally disrupted and rupture in fantastic explosions as the star, as part of the star is pulled towards the black hole, it becomes shredded in a sense. And so you can have funnels of matter that also result from black holes pulling on neighboring matter. So these are very, very intriguing objects, very intriguing objects. And that is, in fact, how we know they exist is through their distortion and their effect on matter. That is how we infer that they are our companions, in the universe.
All right, well, thank you so much for joining us, Jimmy. Again, Jimmy Negus, our grad student from CU Boulder. Awesome to have you on the show. And if anybody has any other black hole questions that get submitted, we might contact you a little bit later and see if we can get an email response. Otherwise, yeah, thanks again for coming and chatting with us. It was really fun.
It's been a pleasure to be on board. Thank you very much for having me.
All right, thanks, Jimmy.
Thanks, Jimmy.
All right, everybody, I am super excited to introduce our next guest, Dr. Andrew Hamilton. He's a professor of astrophysics here at CU Boulder. He's also a fellow at the Joint Institute for Laboratory Astrophysics. He's got interests in relativity and cosmology and, of course, black holes. Dr. Hamilton was also a contributor to the planetarium film Black Holes, The Other Side of Infinity, which we show here at Fiske. It shows at planetariums all across the country. So we're super excited to talk to you today, Dr. Hamilton.
It's a great pleasure, Tara. Thank you very much.
Yeah, thanks for joining us.
So I'd like to kick things off with what to us seems like a very simple question, but is perhaps the most important question of the episode. And this is coming from all sorts of listeners. The question is, what is a black hole?
A black hole is a place where space is falling faster than the speed of light. That's it.
So concise, so straightforward. You said it's where space is falling faster than the speed of light.
That's right. People often say a black hole is a place where gravity is so strong that not even light can escape. But that leads to the question, why can't light escape from a black hole? The answer is a simple one. Space itself is falling faster than light inside the horizon of a black hole. And that's why light cannot get out. You may have heard perhaps that nothing can go faster than the speed of light. The trick is nothing can go through space faster than the speed of light. But space itself, in Einstein's general relativity, can pretty well do what it likes, including pieces of space-time being able to depart from each other faster than the speed of light.
I've
Brilliant.
never
Well,
been that way. That's great.
that is very, very cool. That is awesome. So there we go.
Let me give you a little bit of attribute here. It wasn't me who came up with this idea of space falling faster than the speed of light. It was come up with by two gentlemen, one Alvar Goldstrand and the other Paul Painlevé in 1921. What they did was a piece of mathematics. Curiously enough, they didn't understand the mathematics, and that's very common in the field of general relativity. But nevertheless, they showed, even though they didn't understand it, that space falls faster than light inside the horizon of a black hole. Alvar Goldstrand was a Nobel Prize winner. He won the Nobel Prize in 1911 for his work on the optics of the human eye. And he was on the Nobel Prize committee that in 1921 prevented Einstein from winning the Nobel Prize for relativity. They awarded it to Einstein, not for relativity, but for the photoelectric effect. And Paul Painlevé is equally interesting because he was Prime Minister of France on two occasions for a short amount of time before 1921 and after 1921. So it was an interesting set of folks.
Sounds like, that's very cool.
Yeah, and I think it's really nice to incorporate these kind of historical stories into the science. It makes it a lot more interesting. You said something that actually leads perfectly into another question that we have for you, which is that you've said, as Dr. Andrew Hamilton, that to understand black hole theory, you just have to trust the math. And on the surface, the mathematics in the papers that you've written and in countless others doesn't look too crazy advanced beyond an undergraduate mathematics education. So what is it about the math and the equations that is or seems so challenging to trust in?
So first of all, even though astronomers see evidence for things that look very much like black holes, stellar-sized black holes and supermassive black holes at the centers of galaxies, even though astronomers see these things, we can't go inside, so we can't test them. And so in order to understand what these things are, black holes, we have to understand the mathematics. We have to understand the physics. We have to turn that handle. And a priori, one doesn't know what you're going to get. You don't know what you're going to get before you do the mathematics. I got into studying black holes through visualization. I didn't start off with thinking black holes are cool as a research project. I thought, what happened was I wanted to teach relativity to undergraduates. And for some strange reason which escaped me, undergraduates seem to be fascinated by black holes. And so it was undergraduates and teaching that got me into this role of doing visualizations of black holes, and in particular, visualizing what happens when you fall inside the horizon of a black hole, which hadn't been done before. And it's very interesting because I didn't know what it would look like. I did the mathematics, the equations of general relativity are quite specific. So you knew what equations to solve and you knew how to do the ray tracing, but you didn't know what it would look like. And then when you did those visualizations, it wouldn't look at all like I expected. And in my experience, that is quite typical in general relativity. You do a calculation and you have a preconception of what it should look like. And that preconception isn't borne out by the actual mathematical calculations you do. So if you find yourself sometimes baffled by black holes, and possibly baffled by the mathematics of black holes, welcome to the club, because I'm the first person to admit I'm constantly baffled. It doesn't stop me doing the calculations and eventually slowly figuring out what those mathematical calculations mean. But beforehand, no. I have a success rate of 0% on anticipating what's the right answer.
Fair enough.
I should say I have become more interested in high energy physics and theories of everything in the last few years, because it does seem that in order to understand what's happening inside black holes, in particular in this extraordinary region near the inner horizon where things get banged together at Big Bang energies, to understand the physics of what's happening there, I need to understand high energy physics and possibly theories of everything.
And that kind of perfectly leads into my next question is, as someone who, you know, lives and breathes in this field, where do you see the black hole research sort of going, or where do you hope that research is going in the near future?
I'm going to speak for myself personally. There is a substantial community of astronomers who do real work in real black holes, observing black holes one way or another with various telescopes, optical, X-ray, radio. Nowadays, you've heard about the Event Horizon Telescope, gravitational waves being detected from emergence of black holes, all good, real astrophysicists. I find myself a little bit lonely in trying to study what happens inside black holes. My excuse is that I didn't want to fall inside a black hole, but because I was doing visualizations and taking people through the horizon of a black hole and trying to figure out what happened, my research basically got preempted and has forced me into that area. And I'm very thankful because it's a fascinating area. But I would love to see more scientists interested in black holes. I sometimes hear from my colleagues that the astronomy of black holes stops at the horizon because you can't see beyond the horizon. And there's something to be said for that idea. But on the other hand, what happens inside black holes is, to me, the most interesting question in all of physics, and could potentially lead to an understanding of such things as how our universe was made, how baby universes might be made. Is there a multiverse? What are the laws of physics at very high energies? I think these are fascinating questions which can be answered in a more practical way than just sitting down and trying to dream up new ideas. Nature is already giving us clues with black holes.
And in working with, you know, kids and adults, public audiences, that sort of thing, do you ever find there's any really sort of common misconceptions that you end up clarifying a lot, or things that you especially like to harp
the world of black holes is, I'm sad to say, packed with misconceptions. Ah, dearie me. These are statements that are made often by my colleagues and often repeated in the popular literature. And here I am saying that these are misconceptions. Why? Based on my own authority. Why do I say that? Because I've done the calculations, and I did the calculations expecting to get the standard result, and lo and behold, they didn't agree with what people say. And you've got to believe the mathematics. So eventually you say, oh, okay, I have to revise my thinking here. Let me give you probably the most classic example is a statement that is very commonly made that a black hole is a place where matter gets compressed to an infinitesimal point called the singularity at the center of a black hole. That is wrong. Would you like me to name a list of famous people who have stated that? Never mind. There's a whole bunch of people who say that the singularity of a black hole is a point where all the matter that's accreted into the black hole concentrates into an infinitesimal point of infinitesimal density. Here's the problem. If you fall into a black hole, imagine two people falling into a black hole. And it's a spherical black hole. Let's make it that way, non-spinning. So it has something called the singularity of what appears to be its center. So these two people try to fall in, and they try to fall in at the same time. And the question is, do they meet? The answer is they don't. Because inside a black hole, space is falling faster than the speed of light. So if you're inside a black hole, whichever direction you're looking at, you're always looking at outside your position. So let me take you through this a little bit more carefully. So people ask this question, for example, suppose I fall feet first through the horizon of a black hole. What happens? So you're going to be freely falling. You're not going to be fighting it. You're going to be freely falling. And so your feet fall through the horizon of a black hole. At the moment your feet fall through the horizon, your eyes are outside, so you're looking down at your feet. Your feet are below you. Your feet emit light. And because space is falling at the speed of light at the horizon, the light that your feet emit sits there at the horizon, barreling away at the speed of light through space that's falling at the speed of light. Meanwhile, your head comes down and catches up with the light from your feet. And the question is, do you catch up with your feet? No, you don't. You look down, you still see your feet below you. And if you continue to fall inside the black hole, you look down, you still see your feet below you, but you see an image of your feet as they used to be above your head. Yes? Your feet inside the black hole, your feet emit light upwards, but because space is falling faster than the speed of light, it drags the light downwards like a Michael Jackson moonwalk, and your eyes eventually catch up with that. I want to do a little aside here, and you can edit this. This is something that it seems the community doesn't understand very well, and particularly with regard, for example, to Hawking radiation and quantum gravity. Hawking radiation, Hawking told us, is emitted at the horizon of a black hole. And it seems like many physicists imagine that when you fall to the horizon of a black hole, you will catch up with the Hawking radiation. Well, no, you don't catch up with the Hawking radiation. You don't catch up with the light from your feet, and you don't catch up with the quantum radiation called Hawking radiation. So there's some deep misconceptions about the nature of the horizon amongst the quantum gravity community. Back to where I was. You can just cut all of that out. It was too advanced. Where were we? Yeah. So the light that's emitted inside a black hole has to be falling inwards. And in order for light, for me to be able to, I really want to show you a picture. Am I allowed to show you an image instead? This is getting too complicated.
You can. The trick is that we expect a large portion of the listeners to be listening audio only, so they will not get the experience of looking at the picture. And if we're in over our heads, that's okay. We can kind of back out of this analogy.
Let me see if I can summarize what's really going on. So you've got two people who are falling in at the same time, or at least trying to. But because of this strange business of space falling faster than the speed of light, and I can imagine I'm one of those infallers, and I'm trying to look at this other person here, but because space is falling faster than the speed of light, I'm actually seeing stuff from outside of me. And if I try and connect my light rays to the other person, I find that they connect only when the observer is well away from the horizon, well away from the singularity. So the net result is I not only do not collide with this other person at the center, but I lose causal contact with this other person already well away from the singularity of the black hole. And if we lose causal contact, that means that when we fall to the singularity, we fall to two causally separated pieces of space-time. So the right way to think about the singularity is it's actually a surface. When people fall along different angular positions, they fall to a different point on that surface. The singularity of a black hole is a surface and not a point. If you want to understand what that surface is, you do have to go beyond general relativity. You have to understand quantum gravity. But within the context of general relativity, you can say without any doubt, the singularity is a surface and not a point.
Thank you again so much for being here. It's been a pleasure to have you.
Absolutely.
Thanks for all the work that you're doing for Fiske. It's so fantastic to see you guys doing that. And I must say, I'm terribly impressed, not just with you, but the rest of the Fiske staff and with the Fiske director, John Keller, who, as far as I'm able to see, is doing an absolutely fantastic job of keeping Fiske floating and thriving in these difficult times and getting all of you guys functioning in the best possible way. So thank you to you all.
All right, folks, that's our episode for today. Thank you so much again to our guests, Jimmy Negus and Dr. Andrew Hamilton. Now, these are just excerpts of these interviews. We will air the extended interviews with the full information. Those are going to be available on our YouTube channel and on SoundCloud. Now, come back next week for sure, because we're going to be talking about Mars. We're going to have Andrew Wilkowski, another grad student here at CU, as well as Dr. Dave Brain. Our podcast is available on YouTube, SoundCloud, Spotify, and Apple Music, so be sure to comment, like, subscribe so you don't miss any episodes. We also want to invite you to visit our website, www.colorado.edu/Fiske. There you can see a schedule of our upcoming episodes. We've got the topics, we've got the guests. There's also an option there for you to submit questions to our experts that we can answer on the episode. So if you have any burning questions, you can send us a message either there on the website. There's a form you can fill out, or just send us an email at fiskepodcast@colorado.edu. That's all. Hope to see you next week.